Welcome back, everybody. Mr. Armke with you for Net 125. Today we're going to get into Module 12, IPv6 Addressing. So we have several topics we're going to talk about today, but the general idea is by the end of this we should be able to implement an IPv6 addressing scheme. So we're going to talk about some IPv4 issues and why IPv6 is necessary. We're going to talk about address representation and address types. We're also going to look at what's called a GUA and LLA IPv6 device assignment, so global unicast and link local address. And then we're going to look at IPv6 multicast as well as how to subnet an IPv6 network. So let's get into IPv4 issues first. Now this is something that we've known about for a little while. IPv4 is running out of addresses. IPv6 is the successor to IPv4. And IPv6 has a much larger address space. Instead of 32 bits in length, it holds 128 bits. Now the development of IPv6 also included some fixes for other various implementations that have found their end of the road, if you will. With an increasing internet population, IPv4, NAT, the nature of the IoT, Internet of Things, what we come to rely on now are end-to-end transactions that can be handled between two IP addresses. So IPv6 transitioning has been going on for a while, but has become far more critical as time has gone on. So for the time being, IPv4 and IPv6 will coexist. A number of companies and other organizations have been transitioning, but until that is completed, which will probably still take a couple of years yet, the IETF has created a number of different protocols and tools to help administrators migrate their networks to IPv6. And we've got three primary categories. We can have a network that runs in what's called dual stack, which is where both protocols are run simultaneously. Tunneling is the method by which we encapsulate an IPv6 packet and change it into an IPv4 packet. So we take an IPv6 packet, let's say, and split it in half. And that's going to be two payloads instead of one. And then we run through the same process we would for a data payload to incorporate IPv4 protocol stacking, and then it gets translated at the opposite side. We also have what's called translation. Network address translation 64-bit allows IPv6 enabled devices to communicate directly using a translation technique. So very similar to NAT for IPv4, but it's built for longer addresses. Now tunneling and translation are transitioning to native IPv6 and should only be used where needed. The goal should be native IPv6 from source to destination wherever possible. So this is why dual stack is considered to be a much more effective means until the transition's finished. Now let's look at address representation. How do we look at these things? IPv6 addresses are 128 bits in length and written in hex. Now, they're not case sensitive. They can be written in lower or uppercase, doesn't matter. The preferred format is to write it in 8 blocks of 4 hexadecimal values each. So the shorthand is often x colon, x colon, x colon, x colon, until you reach 8 blocks. We are going to refer to these unofficially as a hextet because they contain 16 bits. So it's a hextet, we use hex from the origination from 6, and then decimal, of course, meaning 10, so 6 and 10 is 16. So the unofficial term is hextet. So 4 decimal values here. Let's look at a couple of examples. We see 2001 0db8 00001111 0000 0000 0200. The thing is, not only is that awkward to say, but it's awkward to write and to read. Were there 2 blocks of all zeros, or were there 3? It's difficult to keep track sometimes, and especially if you're reading a number of addresses for a big block of planning, it can be very annoying to try and get that together. So sometimes it's helpful to be able to find some rules for rewriting them a little bit more cleanly, and we'll talk about that in a moment. The first rule is to remove what's called a leading zero. So this is only leading zeros, not trailing zeros, because then we could make 1,000 or 1000 the same thing as 1 or 100 or even 10. So we don't want to do that. What we want to do instead is only worry about any zeros that are in the front, because seeing something written out as 0010 or 10 theoretically should represent the same thing. The 0 is just there for what's called padding. So we see down here format and type, preferred versus no leading zeros. And we see that the compression is pretty significant. We see that only the first and fourth block remain as they were originally written. All of the rest are able to be condensed down. Rule number 2 is the implementation of what we call the double colon. Now what the double colon does is allows us to replace any single contiguous string of one or more hextets consisting of all zeros. So the example we saw before that had hextets 5, 6, and 7 all represented by zeros can be very easily substituted using the double colon. We can also incorporate this in addition to the leading zero reduction. So from the original address, 2001 remains the same. 0 dB8 becomes dB8. A string of all zeros just becomes a single zero. Now, because we only have one block here in hextet 3, and we have 3 blocks in 5, 6, and 7, we're going to use the double colon there, because it can only be used once within an address. Because if we didn't do that, let's say that we had double colons at position 3 as well as at position 5, which would skip over. In that case, it would be very difficult to understand which is which. We could have 2 hextets in each block, 3 in one and 1 in the other. Which comes first, the 3 or the 1? We don't know. That ambiguity leads to multiple addresses being mapped to the same compressed form. That can't happen. So we can only use the double colon once. Be very, very careful about this. Okay, so continuing on, we see that hextet 3 is reduced from 4 zeros to 1. Hextet 4 is now the same string as it always was, so hextets 1 and 4 have not changed. Now we have the double colon. The double colon basically says everything from the beginning to the end, from this first colon to the second colon, is all zeros. When you get to the end of the address, you're basically going to start writing from the right to the left, and then whatever's in the gap in between, that's what we're going to fill in. So 200 is at the other end of the double colon, meaning that's the last hextet. So that tells the computer, okay, I know what hextets 1, 2, 3, and 4 are, and I know what hextet 8 is. So that must mean that 5, 6, and 7 are all zeros. So I'll be able to fill that in. Now let's look at some address types. Just like we do in IPv4, we've got some different address types that we use to assign for various functions. Our broad categories fall like this. Unicast. This is going to uniquely identify a single host device interface. Multicast is used to send a single packet to multiple destinations, though it's not what we would consider to be a broadcast form. And then Anycast is where any IPv6 unicast address can be assigned to multiple devices. This is where we can send an address to whatever the nearest device is that has that accepting Anycast address. Now note, as I said, that multicast is similar to broadcast. This is because IPv6 does not have a broadcast address. And this is because of the massive volume of addresses that would be generated in order to check an IPv6 broadcast. Now there is an all nodes multicast that essentially gives the same result, but it has to have an idea of how big the network is at that time, because it can't, there's something like, even in a single subnet, 18 quadrillion or quintillion different addresses that are involved. It's a pretty massive count. Now, in order to identify an address a little bit more quickly, we're going to do the same thing we would with CIDR and involve the / prefix. Or rather, it's listed as a suffix, but it indicates the network prefix. That's always a term that I found confusing. When they say prefix, they're talking about the subnet mask starts from the beginning and moves to a certain point. In this case, what we're talking about for IPv6 is generally a /64. That's the most common. Slack uses 64 bits for its interface ID. It makes subnetting easier. 64 is considered to be good practice. It's the standard. Now, IPv6 prefix lengths can range from 0 to 128. Just like an IPv4 address can go from 0 to 32. Now, obviously, certain lengths don't make sense; they're not functional. But that's beyond the point. Semantically, we can say that we can go from 0 to 128. But the recommendation, again, to emphasize, is going to be cutting it in half at 64 bits. Now, unlike IPv4 addresses that only have a single address, IPv6 traditionally has 2 unicast addresses. We've got what's called the GUA, or Global Unicast Address. This is similar to a public IPv4. These are globally unique and internet routable. We also have what's called the LLA, or link local address. This is required for every IPv6 device and is used to communicate locally on the same link. So inside of our same internal network, we're able to use the LLA. LLAs are not routable, and they're confined to a single link. So we can see in the graphic here on the right, we've got different types of unicast addresses: embedded IPv4, unique local, which is going to be our LLA. And then we've got unspecified addresses, loopbacks, standard link local, and then we've got global unicast as well. Now, about the unique local address, we have a similarity to the RFC 1918, which is the construction of A, B, and C private ranges for IPv4, but there are some significant differences. Unique local goes from FC00/7 to FDFF/7, so 8 bits, just about. It's one shy. Unique local addresses are used for local addressing within a site or between a limited number of sites, and they are used for devices that will never need to access another network. Unique locals are not globally routed or translated to a global IPv6. Many sites use the nature of RFC 1918 to hide or secure their network from potential security risks. This was never the idea behind ULAs, but they are there, so just bear in mind that the implementation in this way is not considered standard practice. GUAs are globally unique and routable. Now currently only GUAs with the first 3 bits of 001 or 2000:3 are being assigned. Currently available GUAs begin with a decimal 2 or 3. This is only 1/8 of the total IPv6 address space, as I'm sure you're aware. The global routing prefix in the GUA is the network portion that was assigned by a provider, such as an ISP. The ISP gets their information from a regional internet registry, or RUR, and then we have the ICANN and IANA subsidiary in order to run that together. So it is a hierarchy, just as it is for IPv4, and depending on ISP policies, your global routing prefix may vary. I don't know why they gave us a chicken for the subnet ID symbol, but they did, and I thought that was very funny, so I left it in. Some of the design ideas that PowerPoint does are very amusing, so occasionally I'll leave them in because they made me laugh, so hopefully they do for you too. The subnet ID field is the area between the global routing prefix, so the first 3 bits, and the interface ID. So there's 61 bits that are usually in that subnet ID. Now this is used by an organization to identify subnets within its own site. You know, the global routing prefix is usually far longer than the first 3 bits, but the first 3 bits are obviously dedicated to that. Usually the global routing prefix is only like 1 hextet. So out of the 64, you've got something like 16 that is divided up for the subnet ID. And then the interface ID is the last 64 bits. So this is the equivalent to the host portion of the IPv4 address. It's actually sometimes derived using the MAC address, which is 48 bits in length, and it wedges in the additional 16 bits as necessary using what's called EUI64. Now IPv6 does allow all 0 and all 1 host addresses to be assigned to devices, so network IDs as well as what we would consider to be broadcast IDs can be assigned. The all zeros address is reserved as a subnet router anycast and should only be assigned to routers. It can be done for other devices, but it should not be. Again, some of this is just standard practice that you're going to have to get comfortable with over time. So practice, of course, makes perfect. Now, the link local address allows us to communicate with other IPv6 devices on the same link and only on that link. So that's our local network. That's why it's called a link local address. Packets with a destination or source LLA cannot be routed. Again, has to stay internal. And every IPv6 enabled network interface has to have a link local address. If an LLA is not configured manually, the device will automatically create one, and they are traditionally in the FE80:/10. So it'll be 10 bits, not just 8. Now let's look at some static configuration. Most IPv6 configuration and verification commands in Cisco IOS are similar to IPv4 counterparts. In many cases, the only difference is instead of using IP, we'll specify that it's IPv6. So for specifying an interface address, let's take a look at the graphic in the bottom here. R1 config, so we're on a router called R1. We're in global config mode, and we're going to specify the interface gigabit Ethernet 000. So now we're on the interface, so the config if is in our little bracket here. We're going to type in IPv6 address 2001:db8:ACID:1:1/64. So what we've told this thing now is that 2001:db8:ACID:1 is our quote-unquote network ID. That's our prefix, network prefix. And that our host ID is pretty much whatever's on the last half of the address. Now, because the first 64 bits covers the first 4 hextets, and we've already got those defined, the host ID is all zeros and then a number 1. So this is the first address in this particular subnet that's been established. Now we've got that address assigned. We're going to type in no shutdown and hit exit, and that will configure that interface. Note that it also gives you the idea that you can go ahead and type in the /64 interface as opposed to having to type it out manually, which is what we would unfortunately have to do if we were using IPv4. So it'd be really annoying to have to type out all ones for that, so it would be FFFF 4 times. You know, it'd be quite an extensive mask to have to type each time. So I'm glad they included the / notation. Now on a Windows host, it's a little bit different than working in Cisco IOS, but not by much. We go in the same way we would configuring anything on IPv4. We're just going to use IPv6 instead. So we're going to go into properties. We're going to go to IPv6 instead of 4, and then we'll type in our addresses. The best practice is to use the LLA for the default gateway of the router interface. You could use the GUA, but I don't tend to recommend that. If you're using DHCP or Slack, the automated assignments, LLA will automatically be specified as the default gateway address. Now, if we configure the LLA manually, this lets us create an address that is more recognizable for people, and it's often easier to remember. Now, LLAs can be configured manually using IPv6. We type in the address, and then we put in link local at the end. So in this case, we have the same interface, int gigabit ethernet 0/0/0, IPv6 address FE80:1:1. So what we've done now is we've said FE80 is our primary interface, and then 1:1 or 0001:0001 for our interface ID. No shutdown, exit. The same LLA can be configured on each link as long as it's unique to that link. Common practice is to create a different LLA on each interface of the router to be able to identify which router interface we're passing through. Now let's look at dynamic addressing for IPv6 GUAs. So most devices are going to get GUA addresses dynamically through ICMPv6. So that's the same message control protocol that we would use for version 4, but again, we're specifying version 6. We're going to create what's called a router solicitation message as a host, and we're going to use that to look for routers. So it's just kind of a probe. The router advertisement message is sent by a router to inform hosts on how to obtain a GUA and provide useful information such as network and prefix length. So network prefixes themselves and their lengths. Default gateways, DNS addresses, domain names, etc. The RA can give us 3 different methods for pulling the GUA. Slack with stateless DHCPv6, or stateful DHCPv6 with no Slack. So we've got Slack, no Slack, and then kind of a hybridized thing in the middle. Now, we've talked about Slack a couple of times, probably time to explain what it is, right? So Slack allows us to configure a GUA without the services of DHCPv6. Devices obtain the necessary information from the advertisement messages, and the prefix is provided by the RA, and either the EUI64 method or random generation method is used to create the interface ID. So an RA can instruct a device to use both Slack and DHCPv6. The RA message basically will suggest that devices use the following. Create your own GUA using Slack. This is the router LLA, so your default gateway address. And then the IP or DHCPv6 server will then be given to obtain other information such as DNS server addresses, domain names, etc. So again, hybridizing. Slack uses that automated system to generate, based on your MAC address, your GUA, and then you get your LLA for your default gateway. So that allows you to transition pretty quickly. Now, an announcement message can instruct a device to use stateful DHCPv6 only. Now, stateful DHCPv6 is just like DHCP for IPv4. You automatically get a GUA, prefix length, and the addresses of DNS servers. Now, an RA message here is going to suggest that devices use the following. The router LLA, which is your source IPv6 for your default gateway. And then the stateful DHCPv6 server will then provide the GUA, DNS server address, domain name, and any other necessary information. So the solicitation and advertisement message is going to cycle pretty much the same way. It's just which device are you going to get information from. But it is going to be a game of Marco Polo with a couple of different players. Now, when the RA message is either SLAC or SLAC with stateless DHCPv6, the client has to generate their own interface ID. Now, there's two ways we can do this. What's called EUI64, or a randomly generated 64-bit number. Now, the IEEE defines the EUI, or Extended Unique Identifier, as a process to perform the following actions. The 16th bit value of FFFE in hex is inserted into the middle of the Ethernet MAC address of the client. And then the 7th bit is reversed from 0 to 1. So the 7th bit will fall in the 3rd bit of the 2nd hextet. So C then becomes E in this first hextet, as you can see. So first hextet, 2nd character, we're going to change that from C to E. And then we're going to take the middle, so the division between 47 and 75, and we're going to split it in half and stick FFFE right in the middle. And that's how EUI64 generates these automatic addresses. We're going to take the MAC, flip a bit, and insert a, not a prefix or a suffix, I guess it would be a midfix, in order to generate the requisite length. Randomly generated information, however, is traditionally done as starting with Windows Vista to just make a random 64-bit number that it'll slap on the end. In this case, we see here it's going to be 50A58835A5BB66E1. Now, because randomly generated numbers could possibly be duplicated based on seed time, and if you get into computer science and programming and you look at how we generate random numbers, you see that it's not really random at all. It's just that we use very large primes or seed times based on the system clock, things like that, in order to give the illusion of randomness. There's still a basis for the algorithm of how it's created. Now, to ensure uniqueness at that point, because we could possibly have a duplicate value, we are going to use a process called DAD, Duplicate Address Detection, similar to ARP. It's basically going to ping and say, hey, does this address exist? If there's no response back, the address is unique, we're good. This is why I don't really like random gen RIDs. Not to be offensive, but there is a term that floats around the internet called praying to RNGesus, RNGESUS. And the idea is that you're hoping that a randomly generated number is as good as a hopefully unique number can be. You know, we're hoping that the randomly numbered item favors you. You know, certain games rely on random number generators, etc., for loot division. I like dealing with the EUI method because the MAC address already has to be globally unique. You know, the MAC address is made in two parts, as we recall. We have the vendor ID at the front, the first half, the first 24 bits. And then on the second half, that's the interface ID that was generated when it was made. And because the vendor can only make X number of interfaces one time, there's only one complete MAC address that's going to be set. That's why MAC addresses are global. So inserting that block and then flipping the bit should mean that you're always getting a random address each time. Or not a random address, a unique address. But of course, you know, there's always variations of why people want to use one method over the other. Just letting you know that with that, you are creating some extra overhead because DAD does have to be pinged each time. Now let's take a look at dynamic addressing for IPv6 LLAs. Let's get a little link local there. Now, we've said twice already that all IPv6 addresses have to have an LLA. Like GUAs, they can be configured dynamically or statically. Now, the figure below shows us an LLA dynamically being created using the FE80/10 prefix, and then the interface ID is either using EUI64 or the random process. Operating systems such as Windows will traditionally use the same method for SLAC GUAs as well as dynamically assigned LLAs. You can see here At the top, we can see the EUI64 method, so we see the MAC address with the flip, as well as the FFFE insertion in the middle. And then we see the random generation down below, where the link local IPv6 address as well as the standard IPv6 address have that same random assignment at the end. Now, Cisco routers will automatically create an LLA wherever a GUA is assigned. And by default, Cisco IOS uses EUI64 as opposed to a random generation. Very happy about that. Here's an example of the configuration for G000 and R1. We see that we've got our standard, what's called BIA, or burned-in address, 7079 B392 3640. Okay, so we're going to change from the 7th bit from a 0 to a 1. So that's going to go from a 0 to a 2 because we're changing in that hextet the 3rd bit. So the 3rd bit in a 4-bit number is going to be the representation of 2 to the 1st, or 2. So that becomes 72. So let's check down here. 7279 B3, so that's that first half, FFFE, we see that insertion, 92, and then 3640. So this is the proper EUI method with the FE80 prefix. Now let's look at 12.7, the IPv6 multicast address. With multicast addresses, we start with the prefix FF00/8. Now, /8 tells us that that's 2 hextets, so FFFF, so that's going to be all ones. Now, there are 2 types of multicast addresses in IPv6, well-known and solicited node. Now, note that multicast addresses can only be destinations and not sources at this point. You still have to use the unicast address as your source. Well-known multicast addresses are assigned and reserved for predefined groups of devices. The most common assigned multicast groups are all nodes and all routers. All nodes is FF02:1, and all routers is FF02:2. All nodes is a multicast group that all enabled devices for IPv6 will join. A packet sent to this group is received and processed by all interfaces on the link or network. All routers is one that all routers will join. A router becomes a member of this group when it is enabled with the IPv6 unicast-routing global configuration command. So you're going to go into router, config, or enable, config T, and then you'll type in IPv6 unicast-routing, and that will make it a member of the FF02:2 group. Solicited node multicasts are a little bit different. It's similar to the all nodes address. Solicited node is mapped to a special Ethernet multicast address. The Ethernet NIC can then filter the frame by examining the destination MAC without sending it to the process at IP level to see whether or not the device is the intended target or not. So we can see here the transition in the graphic. The destination MAC lists it as being multicast. The IPv6 is solicited node. So these 3 devices can all be like, okay, this multicast is not for me, this multicast is not for me, and the last one's like, hey, my NIC has determined this multicast is for me. Yet another reason why I like mapping IPv6 generation based on the MAC address. You know, when the MAC and the NIC are able to talk to incoming packets a little bit more authoritatively, I guess let's say, I feel like it speeds things up. Now let's look at subnetting an IPv6 network. IPv6 was designed with subnetting in mind, even as massive as the address space is. There's actually a separate ID field that is specified in the GUA in order to create subnets. The subnet ID field is the area between global routing and the interface ID. So the first 48 bits traditionally is going to be our global routing prefix, as I said before. So that's your 3 hextets. Your 4th hextet is going to be your subnet ID, and that together comes into 64 bits, or half the address, leaving the other half for the interface. Now, given the 2001 DB8 ACAD/48 global routing prefix with a 16-bit subnet, that allows us 65,536/34 subnets. The global routing prefix is the same for all of them, and only the subnet ID hextet is incremented in hex for each subnet. So we go from 1 through 9, and then A through F, and then we move to 10, then 11, 12, so on and so forth. Here we have an example topology that needs 5 subnets, one for each LAN, as well as the serial link going between the WANs at router 1 and router 2. We go ahead and allocate those subnets with subnet fields 0 through 5, and each /64 subnet will give more device addresses than will ever possibly be needed. There is no device that you can create that has enough ports to be able to smash all of those subnets. But it is more so for organization at this point, rather than for actual host meeting of requirements. Now let's look at subnetting an IPv6 address via the router. So here's our router to configure. We've got interface gigabit 000, IPv6 address 2001 DB8 ACID 1:1. Then we've got 2:1 for 001, and we've got 3:1 for 010. In this case, our router only has 2 gigabit interfaces and one serial interface being employed. So here are some new concepts and commands we've learned. Hextet, of course, that refers to a block of 16 bits that represents 4 hexadecimal values that we use to make up 1/8 of an IPv6 address. Link local versus the GUA. IPv6 address, show IPv6 interface brief, Slack, router advertisement, router solicitation, EUI64, and solicited node multicast. That has been chapter 12. I hope that you have found it enlightening. IPv6 is scary to look at initially when you're not familiar with it, but when you see that it's really just a more expanded form of organization, and as long as you follow the recommended standards, you're fine. You know, I mean, you can work with the same prefixes as you would anywhere else. You do have address translation in certain circumstances, but for the majority, you've got more addresses than you could ever need, so you can get a little bit more creative about how you subdivide things, and it's a lot more efficient. You can actually access a device on the other side of the planet with only that device being accessible, just like it was a public IP address in certain cases. If you have any questions, of course, you can email me at jearmke063@cfcc.edu, or contact me on my Google Voice number 239-7814. Other than that, I will catch you guys next class.